Well over 100,000 people have watched a YouTube video from Scientific American that explains why a paper cut seems to hurt so very much. That video suggests that our brains interpret the pressure from a penetrating injury to the skin as pain. Since we can all easily recognize the dramatic difference between the pressure of a pinch and a penetrating cut in our skin, we instinctively know that our body's nervous system must have a more sophisticated way to sense a penetration than this Scientific American video has explained. You might find it more surprising to learn that even now, doctors and nurses who provide surgical and anesthesia care commonly will answer the question, how does the body know it got cut? Almost exactly the same way Scientific American did in its YouTube video. Indeed, you can today access another video on YouTube that contains another answer, a different answer that embodies the insight we are now going to share with you. That video features renowned British scientist Geoffrey Burnstock, who unraveled most of this mystery back in the 1970s. Burnstock's video does not, however, bear a title that would suggest that it talks about why a cut hurts. Instead, it has the title, Therapeutic Outcomes, ATP. Burnstock's video wouldn't pop up if you were searching on the internet for a reason a cut hurts. But before you fire up your computer to watch his video, please allow me to give you an overview of the topic. Burnstock discovered a previously unrecognized chemical signaling system in humans that utilizes the cellular energy molecule ATP, adenosine triphosphate. You learn about ATP in basic biology. Who would have thought that this molecule, so ubiquitous in the cells of our body, could actually be doing two very important and very different jobs? Indeed, many of Burnstock's fellow scientists strongly resisted his hypothesis of a signaling role for ATP well into the 1990s, when the molecular structure for the receptors for extracellular ATP were finally worked out. Today, in hindsight, it would seem quite obvious that the ideal messenger molecule to signal injury to cells would have a high concentration inside all cells, but a vanishingly small concentration outside of the cell membranes of normal, intact cells. ATP fits that profile. Injured cells, on the other hand, would spill such a molecule into the extracellular space, and receptors on nerve endings that fit the spilled ATP would fire. The action potential from that nerve would notify the brain that body tissues were being injured. We call that notification pain, and pain should cause some protective response, like we get the heck out of there, we fight back, or we call 911. Pretty clever, right? Burnstock called this system of sending messages with ATP Purinergic Signalling. The system uses a variety of P, or purino, receptors because in different areas of the body, the ATP message may convey something different from the pain message. The P2X3 receptor appears to be the most important purino receptor for acute pain, such as the pain of surgery. The understanding of the entire array of receptors gets quite complex. As you might guess, the pharmaceutical industry has made large investments in creating molecules that will block various purino receptors. And indeed, such blockers are headed toward clinical applications. For example, a P2X3 antagonist is undergoing clinical trials for the treatment of knee pain from osteoarthritis. Anesthesiologists cannot help but wonder if our understanding of these receptors might lead to the ability to prevent post-operative pain, creating a totally new form of analgesia. The original miracle of general anesthesia, now over 100 years old, gave man the ability to do wonderful things in the operating room to treat disease and injury. However, discomfort during recovery remains a huge problem. But now we potentially have a new approach. Stay on the watch for articles about P2X receptors and for new information on ATP purinergic signaling, both in the health and disease states. These articles, previously limited to the physiology literature, are now moving into the clinical medicine publications. And do remember that cuts do not hurt just because nerves are sensitive to pressure. Clearly, chemistry is involved in addition to physics.